Right, thank you. Okay. Okay, thank you. So just as a small disclaimer here, I'm just getting over the flu. So, if my nose and throat decides to go rogue in the middle of this talk, just bear with me. Um, so yeah, I'm going to be talking about thermodynamics of planetary building blocks today. Um, and in particular, how they relate to shock experiments and how shock experiments can give us good insight as to how geomaterials behave under extreme conditions. So first, shock experiments in planetary science. These are extremely useful for studying natural phenomenon. Impacts are one of the most common ways that we process material in the early solar system and today. And so this can range in impacts from the small impacts that we see today that very minimally thermally processed material all the way to these catastrophic planet destroying impacts. And so being able to categorize and understand what happens to materials under those kinds of conditions really helps us to understand how planets grow and evolve. And so in particular, geologic materials require experiments due to their behavior and natural scatter. So in comparison to some other materials like metals, geologic materials are just less predictable. And inherently, rocks and minerals have a natural scatter to their composition and therefore to their behavior. So being able to fully understand how they behave is really critical for understanding and being able to model them. So what kinds of questions can we address? So again, how do geologic materials behave under extreme conditions? How do phase changes affect the energy budget of a system? So phase changes are energetically very expensive. So being able to have a better sense of what is that energy budget and when do these phase changes occur allow us to better understand the system. And then what is the post-impact temperature and how much melter vapor is produced? So not only being able to constrain the shock temperature, but also that post-shock temperature to see what kind of a system are we left with after an impact, as well as how much material has been melted or vaporized, allows us to place constraints on chemistry and what kinds of materials are chemically available after an impact. And again, all of this giving us insight as to how is it that planets are growing and how do they change. So I'm going to be touching on two pieces of work. So the first are some gas gun experiments that we've done on quartz at UC Davis. And then the second are some Z-machine experiments that we've done on the pyroxenes, enstatite, and bronzite, and then a pyrolytic composition glass. And so what I just want to note here is that these are very different types of geomaterials if you're not super familiar with minerals. But so essentially they're sort of sampling very different regimes. Quartz is something that would find in abundance in very thermally evolved bodies. So this is something that we're thinking of on like the surface of a planet like Earth, whereas pyroxene and then a pyrolite composition, those are more mafic, which means that they're less thermally evolved. And so those are like minerals that we would find on planetary interiors or sort of like younger bodies. So jumping into part one here, so the gas gun experiments on SiO2. So this is a picture of the gas gun lab at UC Davis. Let's see if I can do. Can you see my mouse?
Yes.
Okay. So this far gun is our single-stage gun, which can reach impact velocities of about 2.5 kilometers per second. And then this closer gun is our two-stage gun, which can reach impact velocities of about 7 kilometers per second. These impact velocities are really useful for studying materials that undergo phase changes, so solid-solid phase changes, as well as melting. So in silicates, we're thinking of tens to low 100 GPa. And so again, this is sort of like those lower to mid-range pressures, not necessarily planetary interiors or large impacts. So the gas gun experiments we did were all on our two-stage gun. So this is the schematic of our two-stage gun, where we had a powder breech with a hydrogen fill. So essentially, we loaded a bunch of gunpowder into the breech, which propelled a piston into this first barrel that was full of hydrogen gas. That piston then compressed the gas up to the central breech, where the barrel tapers, and then there is a second projectile. The gas pressure in the piston then propel a smaller metal projectile down to the target chamber. So this is a schematic of what our samples look like. So this is our metal projectile. All of the projectiles were stainless steel. And then that projectile strikes our target, which is a metal plate. So these are all metal on metal impacts, which then generates a shockwave that passes through our sample. Our samples were all SiO2, so either crystalline quartz or a fused silica glass. And then all of our diagnostics are looking at this downrange side of our sample. All of our experiments had peak shock pressures between 55 and 125 GPa. And we were focused on taking temperature measurements. Temperature measurements are really useful for information on heat capacity, phase changes, and just generally speaking, it's a useful quantity for understanding microprocesses and just really being able to categorize what's happening to a material while it's under compression. So we're considering a few different cases. So again, we have a crystalline and an amorphous sample, and we're looking at them with melt on release, so meaning that they shock into the solid region, and then as they decompress from that high pressure state, they melt. Material that is superheated, so it's in a metastable solid phase, and then melts on release, and the material that is shock melted, so it's shocked past the melt curve into the liquid region, and then it releases also to a liquid state. I'm going to touch a little bit more on that later with a phase diagram, so you can see where those all are sitting. So again, one of our primary metrics here was temperature. All of our pyrometry were fiber-coupled systems, and we used direct calibration methods, which means we don't use any in-situ references. The first system was a 4-channel near-infrared INSPI system. And so these ranged from 1.5 to 5.5 microns in wavelength. And so they're all single bandpass filters. And so this is spanning a pretty wide range of wavelength space. And so these detectors are pretty straightforward. They have an indium antimony chip that when they're exposed to infrared light, they create a current. And so we're able to relate that current that it generates to a radiance that it observed. The next system is a streaked visible spectrometry system, or an SVS. And that ranged from 300 to 800 nanometers. And the SVS, I have a cartoon. So essentially light comes in from the gun via fiber optics into our spectrometer, where it then is organized by wavelength. And so we have wavelength resolved light that then goes into our streak unit as photons. Those photons strike a photocathode, which then converts them to electrons. And then in this inner streak tube, those electrons are in an induced magnetic field, which then streaks those, my mouse, which then streaks those electrons across this phosphor, and it glows. And so over time, we're able to have this time and wavelength resolved data that the CCD camera then takes a photo of, and we're able to relate the number of counts to how hot the sample was. So one of the benefits of having this very wide wavelength system is that some of our wavelengths have material that is not absorbing. So in the visible spectrum, SiO2 is not absorbing. It's almost entirely transparent, whereas in the infrared, it's actually very absorbing, especially as we get to these longer wavelengths. And so looking at this plot over here of fused silica transmission, so you can see in these two bins here, which are these shorter wavelength NIR detectors, it's very close to 100% transmission, But as we get further down, we get to almost 0% transmission. And so being able to pair data that is not absorbing to data that is absorbing is really helpful. But also having absorbing data means that we can utilize all the different features of the data. And so as an example, this very absorbing band gives us really high quality release temperatures. So there isn't any light really coming from the solid that is going to obscure the release temperatures. Whereas in some of our other bands where basically there isn't any absorption, we may have some muddled data. And so we are able to use all of this data to its full potential. But we do need to account for this variable absorption. And so for the infrared, we use a method described in LUO 2004, where essentially you have to measure the unshocked absorption for each sample. And then you fit this function to determine the true radiance as well as the shocked absorption. So this is the corrected radiance. So this is the radiance that we want to get. This is the observed radiance of our sample. This term collects all the different reflectivity corrections. These are done before we get to this function fitting, but I can talk about that more later if anyone's interested. And then we have this unshocked and shocked absorption coefficients. So essentially, as the shock wave is passing through a material, there is material obscuring the light in front of it. And so this is calculating as that shock wave is propagating through, how much light is able to get through. And so that's what this correction looks like. So going from the 1.8 micron channel all the way to our 4.8 micron channel, where the 1.8 is less absorbing and the 4.8 is most absorbing. You can see the differences in the shapes of the data. So these are all the different shock regions. So for our two channels that are the least absorbing, you can see that they start to plateau towards this end region of the data. This wiggle in the beginning is just the response of the detector. It's not actually data. But this end of the curve here is the actual light that we're seeing coming from our sample. And it starts to plateau. In this sort of mid-absorbing example here, you can see that the slope is a little bit steeper, and then eventually with this very absorbing channel, the concavity changes. And a lot of the light is being obscured. And so not only are we skipping the detector wiggles in the beginning, but also there might be some light coming from our metal driver. And so skipping all of that and just fitting to this last about 1/3 of the sample is what we're going for. That ensures that not only are we only seeing the actual detector response or the actual detector measurement rather than the response, but also that we're not getting any other light. Next, looking at the SVS. So in comparison, again, the SVS has very minimal absorption, so it's actually pretty straightforward to analyze, especially for quartz. Quartz is really well behaved in the visible spectrum. There are previously measured reflectivities. It's a temperature standard, so we have a lot of references to go off of, but essentially we can use reflectivities that have been previously published from Hicks 2006, and then there's negligible absorption. So essentially all we have to do are camera corrections. And so in this case, you can see the red regions are where we have more counts and the blue regions are fewer counts. And so where we have more red and orange and yellow, those are hotter regions, and then the blue are cooler. And so here we can see we have the shock region that's very bright, and then this post-shock region that is a little bit cooler, and then this big red splotch, which is our fiber being struck. And so we could take temperature out from the SVS and fit it to a black body, but instead, essentially all we do, because we have this time and wavelength resolved data, we basically take a representative region from the shock and the post-shock, and we fit that data to the corrected infrared. And so we fit a Planck function to find an equivalent gray body. So these are corrected radiance data rather than uncorrected gray body data. And so fitting a Planck function to our data is how we find the final temperature rather than taking temperatures from individual detectors. And so you can see here the infrared channels and then our streak. And so this is a black body function found using a Monte Carlo. And so the temperature with air is found using this Monte Carlo fit rather than taking this average temperature. And so one of the benefits of doing it this way is that it's actually makes our temperatures a little bit less sensitive to some of those like user-defined parameters or quantities that we just can't measure in the lab. So it makes it a little bit less sensitive to some of the potential issues or, user-adjusted things that could potentially create an issue. And also it does help to constrain our errors a little bit. You can also see that the errors on the infrared tend to be a little bit smaller than the errors on our SVS. And so it also means that we're a little bit less sensitive to some of these large errors in a single channel or even just a single region in our SVS. So talking about quartz, so again, the samples were crystalline, Z-cut alpha quartz, and amorphous fused silica glass. And again, pure SiO2 is not particularly common naturally. We do have regions on Earth that are abundant in silica and have high silica contents. So, like the continental crust is very rich in silica. And many of the minerals in the crust have a large quantity of silica in them. But at the same time, there's lots of regions on Earth that have low silica content, like all of the oceanic crust. So SiO2 is a good proxy for continental crust. However, just in terms of understanding the context here, it's not the best material for making general statements about planets. So this is more for a specific case of an evolved body or thinking of it in the use case of shock experiments, where it's often used as a standard. So looking a little bit at previous work, there's been extensive work on quartz. It's considered the standard for temperatures. And a lot of work has been put into making fused silica an equally useful standard. But both of these materials pass through a number of multiple solid phase changes prior to melting. And all of these standards really tend to start once these materials have melted. And so having a better understanding of what's happening as they melt and right before that is really important to understanding the full EOS of these materials. So zooming in on this region where they are melting. This is just a simplified version of that little box. So the data in here are from Boslow. These are the same data in Lysinga and Ahrens. And so this is the principal Hugonio for quartz. And so I have these two branches noted, a superheated solid and a liquid. So we have this equilibrium phase, equilibrium melt curve. And the principal Hugonio passes through it and continues on, and then drops down and then continues on as this liquid branch. And so material that's down here, so the Hugonio continuing down below the melt curve, so that material is in the solid. But as the Hugonio continues past the melt curve, it's in this metastable superheated solid region. It still falls along this solid branch of the Hugonio, but it is past its equilibrium melt curve. And then once it melts, there's a drop in temperature and density, which results in this pretty sizable kink in the Hugonio, and then it continues as liquid. And so going back to those three cases that I had mentioned at the beginning, so the solid material that melts on release is below the equilibrium melt curve. And so again, it shocks into the solid region, and then once it decompresses, it melts. Material that's in the superheated solid is past the melt curve, but not past the superheating kink. And then once the material passes this kink and is on the liquid branch, then it's shock melted, and so there isn't a phase change as it releases. Excuse me. Okay. And so being able to understand what's happening as this material is going through this phase change, as well as what's happening in the superheated region, is really helpful for being able to develop this multi-phase understanding. Oops. Okay, so looking at the results, so first of all, we're looking at a temperature entropy plot, and these purple squares are the quartz data, and then these blue circles are the fused silica data. This is a temperature entropy plot, so this is helpful for seeing the relationship between the shock and the post-shock states. So essentially, the other way to think of this is more or less you can think of this as going from low to high pressure, if you prefer to see it that way. But so these orange triangles are from Luo 2003. So these are the same data as Boslow and Lysinga and Ahrens, but these temperatures are calculated rather than measured. They're pretty similar, but I'll touch on the calculated temperatures in a second. But so there's pretty good agreement between our data and these previous data. We're seeing this superheating kink in about the same location. But looking at the vapor dome, so again, this is an entropy plot. So there's an isentropic release. So if you find a point right below it will be the shock and post-shock corresponding temperatures. And then this is our liquid vapor phase boundary. But so there seems to be some kind of a preference in our data for the liquid vapor phase boundary fit. So this gray curve is from Krauss 2012, and then this red curve is the anios liquid vapor phase boundary. And so for the most part, these liquid points seem to prefer this gray fit, but these points that are in the solid seem to prefer the anios fit. So this is perhaps some evidence for a non-isentropic release due to the phase change. So again, the material that is over here is not undergoing a phase change as it decompresses, whereas the material on this side of the curve is undergoing a phase change. But again, this also might just be the case that we're not accounting for some process that's occurring, and so this kink may not actually be the case, but again, there's something that we don't know that's happening if that's true. So next I want to touch on the thermal histories. So these are the near-infrared data. And so something that's interesting is that these thermal histories that we're seeing are very clear in the near-infrared, but they're actually not particularly clear in the visible light data. And so a lot of other studies have looked at visible data, but perhaps it's something to do with optical depth, but the visible data doesn't have the same level of resolution on these thermal histories as the near-infrared. But so first looking at this plot, sorry, there is a gardener right outside my window if you can hear them. So looking at this first plot, these are both crystalline samples, and this first one is shock melted. So you can see this very clear rise into the shock region, and then a drop with temperatures in the release region that are buffered by the liquid vapor phase boundary. And there's a very clear, and again, we have these wiggles. Sorry, my internet is unstable, I guess. But so we see a very clean rise and fall because again, this material is shock melted. It melts while it's in the shock state, and so it does not have to undergo a phase change on release, and it very quickly thermally equilibrates. Whereas looking at this case of crystalline that is melting on release, so this is below the superheated region, we see this multi-stage cooling that happens on release. So there's this shock region, and then what we interpret happens next is that there's an initial release as solid, and then there's this region where the material is melting. And then these temperatures would be buffered by the solid liquid phase boundary. And then perhaps there's another phase change happening here, but there's a local minimum that it reaches. And then these temperatures are buffered by the liquid vapor phase boundary. Again, we saw them in this plot. So all of these points here are that final region right here. And perhaps we're seeing not only temperatures for when these phase changes are occurring, but also how long it's taking these phase changes to occur. And next, comparing the crystalline versus amorphous material. So these are both melt on release, so they're shocked to the solid below the superheated region. They both show very similar shaped thermal histories. The amorphous case is a little bit more subtle than the crystalline case, which just may be due to what phases they are compressing to. Excuse me. But again, they have very similar shaped thermal histories, which again is perhaps providing some insight as to how long it's taking them to undergo these phase changes, but also how subtle and how close these temperatures are to the phase boundaries. And then finally, looking at material that has been superheated versus material that's melting on release. So again, going back to this melt on release case, so we initially think that there is a solid release, and then phase changes have to occur to get us down to this liquid vapor phase boundary. But in the superheated region, this is a lot closer to the way that our shock melted samples look. And so perhaps this is the case because the material is undergoing these phase changes in a very quick and subtle difference, whereas this is a little bit more dramatic. And so temporally, we just don't have that kind of resolution. However, perhaps this is also showing us that the material that is superheated is changing to a different crystal phase that does not have strength as it releases in comparison to the crystalline material that does have strength on release. And so there's some kind of kinetic inhibition to melting in comparison to this superheated case. And so again, being able to understand what exactly is happening as these materials melt is really important for understanding not only where they are in phase space, but also what is happening as these materials superheat. Okay, so I'm going to shift gears here now and move on to the Z experiments. So the gas gun experiments, again, those were a good impact velocity pressure range for understanding what's happening for phase changes and some of those lower to mid-range pressures. And so quartz was a good example case for those kinds of pressures. But when we're thinking of planetary interiors and large impacts, primitive bodies, we want to be thinking of some higher pressures. And so the Z machine is a very good place to do that. And so these experiments were part of two campaigns that combined Z and omega experiments, and then one of them also had ab initio calculations. So I will just note that I'm going to be touching mostly on the Z experiments. I'm going to highlight some of the omega results, but this is primarily going to be talking about Z. And so our goals here were to be taking principal Hugodio measurements with temperature. And so again, we were looking at pyroxenes and pyrolytes. And so for all of the cases, we were doing a setup with an aluminum flyer plate. And so essentially there's a current running through an induced magnetic field that launches a flyer plate with a Lorentz force. And so this aluminum flyer plate strikes our samples. We had some cases where samples were directly struck by the aluminum flyer plate, and they were backed by a window of quartz, TPX, or fusilica. And so those were measuring the P rho hugonios. And then we also had some cases where an alpha quartz window was struck by the aluminum flyer plate, and then that was backed by one of our samples. And so in that case, we were measuring temperature. But so for all of these, we were trying to get these principal hugonio measurements to compare not only the hugonio measurements, but in particular the temperatures between the two different platforms. And so one of the issues that we needed to address with these samples is that we were dealing with samples that had color. So the samples were colored, and they also, some of them had iron in them. And so I'm going to touch on that in just a moment. But one of the problems with colored samples is that inherently that means that they are unevenly absorbing across the visible spectrum. And so Z uses an SVS system, whereas Omega uses an SOP system. So the SVS gives us wavelength and time resolved data, whereas the SOP gives us space and time resolved data. And so without that wavelength resolution, colored samples and iron-bearing samples are very challenging to deal with. And so we needed to be able to address this and account for this coloration to the samples. And so in order to deal with that, we needed to use the SVS's full capabilities. And so again, we use the same method from Luo 2004. This was first employed on the ZSVS in Chittister et al. On iron-bearing olivines. And so again, essentially we want to get this corrected radiance. We take the observed sample radiance, all of our reflectivity corrections, and then we needed to fit for the shocked and the measured unshocked absorption. And so we were able to measure unshocked absorption in the lab, and then fit for the shocked absorption, as well as that corrected radiance. So what that looked like, so this is one of the SVS images. So this first region here is the quartz, and then backed directly behind it is one of our samples. And so again, this is the quartz backed by a sample. And so we took wavelength bins of 10 nanometers each, and we separated out those bins. And so this is going from the shortest wavelength to the longest wavelength. And we separated out those bins and then took a representative region for each of them for the quartz and then for the sample. And then we averaged the radiance across each of these bins. Then we took each of those bins and we performed all of our corrections to them. So essentially we corrected for the absorption. So where whatever wavelength bin we were looking at, the absorption for that bin. And then we also measured reflectivity on Omega in the corresponding experiments. And we made all of those corrections and then did 10,000 Monte Carlo steps. And so each of these ellipses is 10,000 perturbations of each of those bins. And then we fit a Planck function to these radiances. And again, similar to the quartz campaign, we fit to these radiances, which actually helped us to really significantly constrain the temperature in comparison to looking over here, which is for each individual bin, what their average temperature was. For the most part, they had relatively good agreement, but sometimes there was an outlier case, which would have affected our average temperature, but it really didn't make an effect because we had all of these data to constrain our Planck function. So going in on enstatite and bronzite. So these are pyroxenes. They're very mafic. They are abundant in the mantle. And they are one of the most abundant minerals in the mantle. So in the upper mantle, they are present as enstatite and bronzite, but in the lower mantle, they're abundant as bridgmanite. And bronzite has an inherent scatter to its composition. So looking up here, enstatite is the magnesium-bearing end member, whereas bronzite has a solid solution series between magnesium and iron. Excuse me. And so inherently there's a little bit of scatter to the composition. And enstatite has been previously studied, but the iron-bearing bronzite has not. And just inherently, planets are not magnesium-bearing end members, and we need to be able to study these iron-bearing members. And so iron makes the samples a lot more challenging with additional corrections. They have higher reflectivity. They are more strongly colored. The enstatites are very, very lightly colored, but they do still have some coloration to them. However, it's nothing compared to how strongly colored these bronzites are. And so systematically studying these iron-bearing minerals is very useful, especially being able to compare them to their non-iron-bearing counterparts. And then next, the second set of experiments was on pyrrolite. And so pyrrolite is a hypothetical mineral assemblage. And so it represents the mantle or the bulk silicate earth. And so it's mostly made up of olivine and pyroxene. There's a few other oxides in there, but approximately you can think of it as olivine and pyroxene. And so the best direct analog for this is a quenched magma ocean. And so thinking of this as that crust of a magma ocean, especially because these are glass beads. And so these had similar difficulty in that they do contain iron. These are pretty significantly absorbing. They're much more absorbing than the bronzites. And while there is relatively small scatter in the composition, there were some issues with differing optical properties. So looking at this picture here, so these are the pyrrolite beads in crossed polarized light. And so you can see there's these big bands that run through them. Again, the composition is relatively standard. However, these bands could be differences in density. There really weren't any bubbles in them. However, the issues with these bandings is mostly the optical properties changing. And these beads were very, very small, so it was challenging to measure absorption in the beads. However, potentially, given that each bead could have different optical properties from one to another, it does pose an issue. But so these pyrrolite experiments are a good complement to their single mineral counterparts. So again, we were just looking at pyroxenes, and then there has been previous work done on iron-bearing and non-iron-bearing olivine. Plus, the glass is really nice to work with for principal Hugoniot measurements. So now jumping into these results. So first comparing to some previous data. Just to walk you through what these plots are going to look like. So these individual data points are from Z, and then in the background are these fits with error envelopes. So the fits are from omega. They are not taking into account Z data, and the individual points are from Z. And so for the most part, there was pretty good agreement in pressure and shock velocity from previous work, as well as with omega. And so there's a couple of different points back here. So there's some experiments from Fay and Frattantuono. So Frattantuono did single crystal enstatites on omega, and then Fay was doing sort of like a powder microcrystalline bridgmanite on Z. But Frattantuono did measure temperatures on omega, but Fay had simulated temperatures from Z. And so again, relatively good agreement between these previous studies and our current results. However, looking at temperatures, there is a bit of a disagreement between our data and these previous data. So again, these are looking at different starting materials, so there might be a difference in temperature, but our data seem to pretty significantly disagree at these higher pressures. in comparison to especially a single crystal enstatite case. But so for the most part, at these lower pressures, there's some agreement, but we're diverging pretty significantly at these higher pressures. But omega and Z are agreeing on the temperatures we're producing. But looking at specifically these omega fits, it's a little hard to tell in this region where we have Z data, but the temperatures do start to diverge at the higher pressures where the iron-bearing bronzite has a steeper slope hugonio compared to the non-iron-bearing enstatite. But in order to better constrain that, we would need more Z data at higher pressures, but we just don't have that. So it's a little hard to say if it's just within error or if Z is disagreeing with that. So just touching on the scatter and the bronzites. So again, bronzite does have natural variation in the composition. It's relatively consistent from sample to sample, but some slight changes in the composition may be changing the optical properties, which we're not accounting for. And perhaps it's a good example of not using a representative optical measurement, and so instead being able to take individual measurements of each sample. But again, it also may be the case that there's just a little bit of scatter, especially in comparison to the samples used on Z versus omega. And then specifically looking at the differences between the iron and non-iron bearing, the hugonios on both platforms are very, very similar at these lower pressures. And as they start to diverge, again, the errors are overlapping pretty significantly. And so it's hard to say if that's actually being seen. However, the Z data do seem to fall a little bit more significantly along the enstatite temperatures from omega. So it may be the case that, again, because the SOP from omega is not able to account for this uneven absorption and has to use a bulk value, that may be the case that there's some kind of disagreement there. So now looking at the pyrrolite, so these blue points are our pyrrolites. So again, there's some scatter, which may be due to that optical property issue that I had mentioned before. But so these are glass, so we would expect them to be higher composite or higher temperature than their corresponding crystals. And for the most part, that is true. Some of them are pretty similar to these pyroxene temperatures, but the olivine temperatures are basically right below these pyroxenes. So again, higher temperatures for the same pressure. But there is some disagreement between the pyrrolites on Z versus those on omega, but again, it could be an optical property issue. Looking at the densities, so the density actually increases pretty significantly and is very close to these crystalline samples. The density for the enstatites and the bronzites are pretty close to one another, with the iron bearing, of course, being a little bit more dense consistently. But the pyrrolite samples actually increase pretty quickly and match. They're right in between the bronzite and the enstatite densities. And so now looking at comparisons on temperature between Z and omega specifically. So again, these curves in the back are the omega fits, and then the individual points are from Z. For the most part, there's actually very good agreement, especially considering, again, that we just cannot correct for absorption the same way. And these are all colored minerals. Some of them are iron bearing. So there's actually pretty good agreement, considering the completely different pyrometry setups, and they're analyzed completely independently of one another. So just to summarize, again, going back to the SiO2 experiments, so we did those at UC Davis in the shock compression lab, where we were carefully probing the region where these materials melt, measuring shock and release temperatures. And we were looking at thermal histories that suggested where phase changes occur, and where there's potential changes to the material's behavior, like strength versus not strength on release. Then the Z experiments on enstatite, bronzite, and pyrrolite, where we were expanding the principal Hugonios for the iron-bearing minerals and rigorously analyzing the temperatures for colored and iron-bearing minerals by accounting for their absorption. And then comparing that to the Omega results that show very good agreement. And so then just to quickly touch on acknowledgements, there were lots of people involved in this, lots of funding sources. This is all from many, many, many years of work. And so it really would not have been possible without all these people and all of these different funding opportunities. So I'm going to go back here and leave it there.
Thank you so much, Kaitlyn, for an exciting talk. So this talk is